Welcome to our deep dive. Today we're going to be exploring robot mapping. And, it's a topic that you've shown some interest in.
Yeah.
So we've assembled a bunch of resources that are going to help us kind of get into it. And I think it'll be fun.
It is a fascinating field.
Oh, yeah, for sure. And we've got a YouTube lecture transcript.
Yeah.
We've got some articles.
Yeah. And it can seem complex.
Absolutely.
But really, when you break it down, it's very approachable.
Yeah.
So robot mapping, just to give a brief overview, imagine a robot dropped into a completely unknown environment. How does it figure out where it is?
Yeah.
And build a map at the same time?
That's a tough one.
That's the magic of SLAM.
SLAM. Yeah.
Which stands for simultaneous localization and mapping.
Okay, so SLAM, simultaneous localization and mapping.
Yeah.
So it's like figuring out where you are and making a map at the same time.
Exactly.
That sounds really hard. How do they even...
Yeah, it's this intricate dance between a robot's perception of its surroundings and its understanding of its own location.
So, how do you even start with that?
Yeah.
It seems like a chicken and egg thing. You need a map to know where you are, but you need to know where you are to build a map?
Yeah, and that's what makes SLAM so intriguing.
Right.
To really kind of make sense of it all. We need to dive into some of the key techniques.
Okay.
Like Kalman filters and particle filters.
Okay, those sound a little technical.
Yeah, they have kind of intimidating names.
Yeah.
But really the concepts behind them
Yeah.
are very intuitive.
Okay, well, let's break them down then.
Okay, so think of a Kalman filter as a prediction tool.
Okay.
For systems that behave in a mostly predictable way.
Right.
So imagine a robot moving down a hallway.
Mm-hmm.
The Kalman filter uses the robot's motion commands and sensor data to estimate its position,
right? Even
accounting for some sensor noise.
Oh, okay. So it's kind of like, it's got like a dead reckoning system.
Exactly.
But it's also aware that there might be some errors.
Right.
Okay, cool.
Yeah. So it's kind of like a sophisticated dead reckoning system with a built-in awareness of potential errors.
Gotcha. Okay, so then where do these particle filters come into play?
Particle filters are the stars when things get more unpredictable.
Okay.
So imagine our robot encounters an unexpected obstacle in the hallway.
Okay, like a chair.
Like a chair, exactly.
So, or, a dog.
Or a dog, right?
Yeah.
A particle filter can handle this uncertainty by generating multiple hypotheses about the robot's location.
So it's like, I think I'm here, but maybe I'm here. Or maybe I'm here.
Exactly. It's trying out all these different possibilities.
Right.
And then refining those hypotheses based on incoming sensor data.
Okay. So as it gets more data.
Yes.
It's like, okay, well, these ones are wrong.
Exactly. It starts to narrow down to the most likely location.
Okay, cool. So we've got these filters that are helping the robot figure out where it is, but how does it actually build a map?
Right. Well, that's where things get even more interesting. And the YouTube lecture actually emphasizes hands-on implementation.
Oh, yeah.
So why is that so important for understanding these algorithms?
Yeah, why the focus on actually building the code?
You can read about SLAM algorithms all day long, but until you try to implement them, you don't really grasp the nuances.
So it's like one thing to read about it in a textbook.
Yeah, it's very theoretical.
But it's another thing to actually be like, okay,
exactly.
Now I have to make this work.
Right. And that's where the learning really happens. I remember once when I was coding a path planning algorithm, my robot kept getting stuck in a corner.
Oh, no.
And it turned out I had a tiny error in my distance calculations.
Wow.
Something I never would have caught just by reading about the algorithm.
So all that time you spent banging your head against the wall trying to figure out why your robot was stuck in a corner.
Exactly. It was frustrating at the time, but it was a valuable learning experience.
So those hands-on struggles really make a difference.
Absolutely. They force you to grapple with the practicalities of translating theory into working code.
And that's where the aha moments come in.
That's where the real aha moments happen.
Okay, I like that. So we talked about these SLAM terms. I've heard SLAM front end. I've heard appearance-based approaches, and then connect-based SLAM.
Right. A lot of jargon.
Yeah. So can we break those down a little bit?
Absolutely. So the SLAM front end is like the robot's sensory interpreter.
Okay. So it's taking all that data.
It's taking raw data from sensors like cameras and LiDAR and extracts meaningful features.
So it's like making sense of the world.
Yes. It's identifying things like edges, corners, distinctive objects.
Okay.
Things that it can use to build a map.
Gotcha. And then appearance-based Connect-based approaches.
Those rely on visual information to build the map.
So it's like recognizing
patterns or landmarks.
Like we do, like, oh, I know that building because it's got the funny, gargoyle on the front.
Right. And then there's Connect-based SLAM.
Right. The Connect.
Which uses the Connect sensor, originally designed for gaming.
Right. I remember
to create surprisingly detailed 3D maps.
Oh, wow.
And the Connect was relatively inexpensive.
Yeah.
So this kind of 3D mapping is more accessible than you might think.
Well, that's interesting. So even if you're not like some big research lab.
Right.
You can still get involved in this.
Exactly. It's opened up the field to hobbyists and researchers who might not have access to high-end equipment.
Cool.
Yeah.
So, okay, we've got this like foundation of SLAM and the filters and the front-end processing.
Mm-hmm.
There's another concept that I'm kind of curious about, and that's loop closure.
Loop closure. Yeah, that's a crucial part of ensuring the accuracy of a robot's map.
Okay.
It's all about recognizing places you've been before.
Okay.
Even if your sensors are giving you slightly different readings.
Oh, so it's kind of like...
Think of it like this.
Yeah.
You're exploring a room, and you come back to your starting point.
Right.
You need to be able to recognize that you've completed a loop.
Okay, so it's like when a robot's like exploring and it comes back around, it's like, oh, I've been here before.
Exactly.
Gotcha.
Loop closure helps the robot correct for those inevitable little errors that accumulate as it moves around.
Because sensors aren't perfect.
Exactly. Sensors are never perfect.
Yeah.
And it's a bit like how we humans use landmarks and memories to reorient ourselves in familiar environments.
Okay, so it's like if I'm walking down the street and I see that coffee shop, I always go to.
Right.
I know where I am.
Exactly. You have that loop closure.
Gotcha.
Oh.
Okay. But that sounds like a pretty complex challenge for robots.
It is. It requires the robot to compare current sensor data with its previous experiences.
So it's like remembering everything it's seen.
In a way, yes.
Wow.
And sometimes across very different viewpoints or lighting conditions.
Oh, right, because if I see that coffee shop at night, it might look different than it does during the day.
So researchers are developing these sophisticated algorithms that enable robots to extract unique features from their surroundings.
Okay.
Like the arrangement of objects or the texture of surfaces.
So it's not just about matching images perfectly. It's more about like understanding.
It's about recognizing the underlying structure of the environment.
Right. Okay, that makes sense. Now, we talked about Connect-based SLAM being really accessible, but are there limitations?
Yeah, there are definitely limitations.
Especially compared to the, like, really high-end, expensive systems.
Right. Well, Connect-based SLAM has opened up amazing opportunities.
Yeah.
It does have its limitations.
Okay.
Connect sensors are primarily designed for indoor environments.
Okay.
And their range and accuracy can be affected by factors like lighting and surface reflectivity.
Oh, so if it's too bright or too dark.
Exactly.
It might not work as well.
Or if the surfaces are very reflective.
Oh, I see.
Like mirrors or glass.
Okay.
That can cause problems for the Connect sensor.
Gotcha.
So for applications like self-driving cars or aerial mapping, more robust and expensive sensors like LiDAR are typically used.
So Connect-based SLAM is kind of like a good entry point?
It's a great entry point for learning and experimentation.
Yeah.
But for those really demanding applications, you need to step up to more sophisticated technology.
Yeah, okay, I get it.
Yeah.
So we've been talking about these like different systems and how they work, but what about the applications? Like, what are some of the real-world uses of SLAM?
Oh, the applications are incredibly diverse.
Yeah, because I know the sources mentioned self-driving cars.
Right.
Mars rovers and search and rescue missions.
Exactly.
Those seem like really different things.
They are, and that really speaks to the versatility of SLAM.
Right.
So let's start with self-driving cars.
Okay.
For a car to navigate autonomously, it needs to know exactly where it is on the road, understand its surroundings, and be able to plan a safe path forward.
Yeah.
All while things are moving around it.
Yeah, that's a lot.
SLAM is at the heart of making that possible.
So how does it actually help with all of that?
SLAM algorithms allow the car to perceive its environment,
Okay.
identify landmarks like traffic signs and lane markings, and build a detailed map of its surroundings.
Gotcha.
This map is constantly being updated as the car moves.
Oh, wow. So it's like...
enabling it to plan its route and avoid obstacles.
It's like building the map as it goes.
It's a continuous feedback loop between sensing, mapping, and decision-making.
Wow. It's pretty crazy. And what about the Mars rovers?
The Mars rovers are a testament to the power of SLAM in exploration.
Right, because they're driving around on Mars.
Exactly.
Making decisions.
They use SLAM to navigate treacherous terrain.
Right.
Avoid hazards and choose the most scientifically interesting paths to explore.
Go.
And remember, these rovers are operating millions of miles away from Earth.
Yeah.
So they need to be highly autonomous.
There's no one there with a joystick being like, go left, go right.
Exactly. They're on their own.
Wow. That's amazing. And then search and rescue.
Yeah, search and rescue is another really important application.
So like in disaster zones.
Exactly. In disaster zones, robots equipped with SLAM can be invaluable.
I've seen footage of that.
They can navigate collapsed buildings or other hazardous environments, creating maps of the area and helping rescue teams locate survivors.
Yeah, it's incredible what they can do.
They can get into places that would be too dangerous for human rescuers.
Sure.
So SLAM is really pushing the boundaries of what robots can do in the real world.
It's pretty amazing stuff. So we've talked about a lot here.
We've covered a lot of ground.
Yeah, the fundamentals of SLAM, loop closure.
Yes.
All sorts of applications.
And we've only just scratched the surface.
Oh, really?
SLAM is a field that's constantly evolving with new research and applications emerging all the time.
Okay, so there's even more to learn.
There's always more to learn.
I'm definitely feeling inspired.
That's great.
But before we wrap up, I want to go back to something we talked about earlier.
Okay.
Which was using SLAM to map abstract concepts.
Ah, yes, that's a fascinating idea.
Yeah. It really captured my imagination.
It's a very thought-provoking concept.
So we've been talking about robots mapping physical spaces.
Right. Hallways, rooms, streets.
Yeah. But what if we could map something like the spread of ideas through social networks?
Exactly. That's the challenge.
Yeah. How would we even begin to do that?
It would certainly be a challenge.
Yeah.
But I think the core principles of SLAM could still apply.
Okay.
Instead of physical sensors, we might use data mining techniques.
Okay.
To gather information about how people interact and share information online.
So we're like looking at how people are talking to each other online.
Exactly. We're collecting data on those interactions.
Right.
And then we could use SLAM-inspired algorithms to create a map of how ideas flow through those networks.
So instead of mapping hallways and landmarks,
we're mapping connections and influences.
Wow. So we're like creating a map of the intellectual landscape.
Exactly.
That's a really cool idea. Is anyone actually doing that?
There are researchers exploring this idea.
Really?
It's a relatively new area of research.
Okay.
But some fascinating work is being done at the intersection of network science, data mining, and artificial intelligence.
So it's like a whole new frontier.
It's a very exciting frontier.
That's awesome.
Researchers are using SLAM-like techniques to map things like the spread of misinformation online, the evolution of scientific thought, and even the dynamics of political discourse.
So we can actually see how these things are changing and evolving over time.
Exactly. We can track the flow of information and ideas.
That's incredible. This whole deep dive has been amazing.
I'm glad you've enjoyed it.
We learned about the technical details of SLAM.
Right. The algorithms, the sensors.
We saw how it's being used in all these different fields.
From self-driving cars to Mars rovers.
And then we even got into this philosophical discussion about mapping abstract concepts.
It's been a very wide-ranging conversation.
Yeah, it has. And, you know, what's really fascinating to me is that in the process of teaching robots to map the world,
yes,
we're also learning more about how do we map the world.
It's a beautiful feedback loop.
Yeah, it is. So we've gained a deeper appreciation for the power of robot mapping and SLAM. Not just as like a technological marvel, but also as like a window into our own human experience.
It's a reflection of ourselves in a way.
That's a great way to put it. So thanks for joining us on this deep dive into the world of robot mapping and SLAM.
It's a pleasure.
Until next time, keep exploring, keep learning, and keep those curious minds engaged. Okay, so we've been talking about robots mapping these physical spaces.
Right.
But then we got into this idea of mapping like abstract concepts. And that's something I really wanted to circle back to because it really blew my mind.
It is a fascinating idea.
Yeah. So we've been talking about robots mapping hallways and rooms and streets.
Right. Physical spaces.
But what if we could map something like the spread of ideas through social networks?
It's a whole different kind of mapping, isn't it?
It is, yeah. How would we even, how do you even approach that?
It would be a challenge, for sure. But I think the core principles of SLAM could still apply.
Okay.
So instead of physical sensors like cameras and LiDAR,
Right.
we might use data mining techniques.
Okay, to gather information.
Yeah, to gather information about how people interact and share information online.
So, like, we're looking at how people are talking to each other.
Exactly.
So,
We're looking at their posts, their comments, their likes,
right.
all of that.
And
then we can use those SLAM-inspired algorithms
right.
to create a map of how ideas flow through those networks.
Oh, wow.
So instead of mapping hallways and landmarks,
yeah.
we're mapping connections and influences.
So it's like creating a map of the intellectual landscape.
Exactly. A map of how ideas spread and evolve.
That's so cool. Is anyone actually doing that?
There are researchers exploring this idea.
Really?
Yeah, it's a relatively new area of research.
Okay.
But there's some really fascinating work being done at the intersection of network science, data mining, and artificial intelligence.
So it's like combining all of these different fields?
It's a very interdisciplinary field.
That's awesome.
Yeah, researchers are using these SLAM-like techniques to map things like the spread of misinformation online.
Right.
The evolution of scientific thought.
Wow.
Even the dynamics of political discourse.
So we can actually like see how these things are changing and evolving over time.
Exactly. We can track the flow of information and ideas in ways that we never could before.
This is incredible.
It's really exciting research.
Yeah, this whole deep dive has been amazing.
I'm glad you've enjoyed it.
We learned about the technical details, the algorithms, the sensors, the filters.
Yeah.
We saw how it's being used in self-driving cars on Mars.
In all sorts of different fields.
And then we even got philosophical with it.
A little bit, yeah.
Which I love.
It's always good to think about the bigger picture.
It is. And you know what's really fascinating to me is that, like, in the process of teaching robots to map the world,
right,
we're learning more about how we map the world.
Absolutely. It's like we're holding up a mirror to ourselves.
Yeah, that's a great way to put it. So, like, we've gained a deeper appreciation for the power of robot mapping and SLAM, not just as a technological marvel, but also as like a window into our own human experience.
It's a reminder that technology is often a reflection of ourselves.
Yeah, and our own curiosity.
Exactly.
So thanks for joining us on this deep dive into the world of robot mapping and SLAM.
It's been a pleasure talking with you.
It has. Until next time, keep exploring, keep learning, and keep those curious minds engaged.